This video clip will be the demonstration of showing the cable subjected to the uniformly distributed force. The cable that in our question is cable OAB, okay, and the cable have the pin support on the top of the column. The model that we show here, that I'm showing here, actually is have the real structure in the US, as I show in this picture. Is the picture of the George Washington Bridge across the Hudson River between New York and New Jersey. This bridge have the span of 2,300 foot. That is 700 something meter. That's quite long. It was twice as long as any other suspension bridge when it was completed in 1931. So this bridge is one of the big bridge, okay, advances in our civil engineering construction in the past. And if we compare this bridge, this George Washington Bridge, with our model, you may see this structure can be this column, okay. And also there is another structure here for this column. For the real bridge, there is two cable on the left and on the right. Our model, we just take one way, so we only consider only one cable. And then when we do the load distribution, the load half will distributed to this cable and another half distributed in this cable. So our cable will take only half of the real force in the girder, okay, and then the load transfer across the hanger, okay, across the hanger. This called girder, and this called the hanger again, and the cable is here. This is going to be the cable, and you may see the cable hang from the top. Okay, the top here usually is the pin and lay itself across the span of the bridge and up until this point, which also the pin. And this kind of suspension bridge has symmetry at its middle span due to they use the same level of support. Okay, so under the apply of the force under the traffic load, after the life load moving here, including the lead load, okay, the force assumed distributed over here with W sub O, and mean is subjected to the uniform load, okay, and the shape of the cable is in the parabolic shape, okay, and if you may remember, that's be in the form of y equal to the uniformly distributed load divided by 2 times horizontal force and times x squared. What is the horizontal force? Horizontal force, that's the force that act horizontally, okay, usually they always equal what every point that you are considered in the cable. That's we have it in the lecture already, okay. And one more thing about the cable that I should mention, the Tmax occur at the cable that has the angle maximum with the horizontal axis. Most of Tmax occur at the top of the support, okay, and the T-min gonna be here. So from this bit, T-min gonna be over here, and T-max gonna be here. And the rest of the cable, that means this one is going to be another problem that we will calculate later. So what I'm talking about is I'm trying to link between the real structure and what we going to model it for our computation. Okay, let's us go to the example that we have here. The structure shown here is the same model that we just discussed. The cable is the steel cable used to support very stiff girder. As I mentioned, we have the girder that support the load on the bridge. Okay, that is the girder. That is the very stiff girder of the suspension bit. This structure is symmetry. It said it's symmetry. Okay, that means it have the same level of support on the top of the column, about point O, and it's pin at A, and it's pin at the support B, and the force applied to it is the uniformly distributed load of 10 kilonewton. That is for a cable. So actually for the two cable, that's force that's uniformly distributed load gonna be the total of 20. Okay, that is 20 kilonewton per meter, but divided by half. So the uniformly distributed load is 10. And then the span of this girder, the L is going to be 100 meter. Okay, and it have the sag over here of 10 meter. They asking us to do what? First, they asking us to find the magnitude of the tensile force at the x of 30 meter. Okay, before we go further, we have the origin of this cable here. This is x, and this is y. That means the coordinate here is 0, 0. And since this one is 50 meter, so you go here for 50 meter, and you go up there for 10 meter. So it's going to be 50 and 10 meter for the coordinate of point B. And if you move to A, the coordinate going to be minus 50 and plus 10. And this is going to be minus 50 and 10 meter. And what they ask us is 30 meter. So they ask us about this distance. That is the 30 meter. So they ask us at about this point what the tension gonna be. And then the another one, they ask us what is going to be the minimum tensile force. And you may see T max, okay, occur at zeta max. That means mostly the T max occur over here. Okay, that is the maximum zeta max with the horizontal axis. And by this T max occur at zeta max, so the T min will occur at zeta min. And now from this picture, okay, you can see zeta max here. Zeta min is going to be here. Okay, this going to be at zeta min of 0 degree is in the horizontal with the x-axis. And then after finish the analysis, they ask us to determine the diameter of the cable with the allowable of 100 megapascal. So this is going to be sigma allow. To design the cable, you got to find Tmax, okay, and then you use Tmax to find the A required, and from the A required you get the diameter. And finally, they ask us to find the vertical component of the force at A. That means they ask us to find this A sub y. Over here is also have the A sub x. So they like us to determine this. Okay, from this we need to draw the model for our problem. What we have the cable that's about 4.5 centimeter apart. So we have this one is point A, and this one is the point B. So this one is the A, and this one is the B, and it's going to span for 100 meter. Okay, and we have at the middle of 1.7 millimeter. So our cable should have this parabolic shape in the form like this. Okay, and the cable also support the hanger, and then you got to put the hanger here, and the hanger connect to the cable and the girder with a lot of hanger to make the distribution of the force to the cable to be uniformly distributed load. Okay, and what we have is over here is going to be the lowest point, and we set this one of origin of the coordinate x. This is going to be the x, and this is going to be the vertical y direction. Okay, and since this is in symmetry, so this is 50 meter, this is going to be 50 meter, and under the applied force, okay, the cable in tension. When the cable in tension by the 10 kilonewton per meter, we got the reaction occur at the pin support. It's going to be B sub x, and it's going to be A sub x. And you may also know that this is going to be F sub h. This is going to be F sub h, since all the horizontal force of the cable are equal. And then at the A, you also have the A sub y, and also have this for the B sub y. So now you get the free body diagram of the cable. You have the cable system, okay, free from the support. And then you have the applied forces of 10 kilonewton per meter. Okay, and you have the unknown reaction, and you have the required length. The sag is going to be 10 meter. Okay, let me remind you the Tmax. Okay, occur at what? Occur at zeta max. And Tmin occur at zeta min. Okay, and also the F sub h is equal, okay, along the cable length. Okay, and then what you supposed to go further? the cable equation. Cable equation is the parabolic equation. It is y equal to w sub naught for here divided to f sub h and x squared. So next step, we supposed to find the coordinate, okay, of each point. This is going to be 0, 0. This is going to be, you go this by 50 and up 10, 50 and 10. And this is going to be minus 50 and 10, as we know before. And from this equation, what we have is, this is going to be 10 kilonewton per meter, and then it's gonna divide by 2 f sub h and x squared. So this equation can be written, it's going to be equal to 10 divided 2 is going to be 5, okay, and divided by f sub h and then x squared. This is the equation of cable. If we know f sub h, we can write the equation, okay, of the cable, and we'll explain the coordinate along this cable length. To do that, we may use the coordinate of point B, and then by using the coordinate of point B. Of B, okay, we may have the y of 10 equal to 5 over f sub h, sorry for that, 5 over f sub h, and what we have is, that is going to be x squared, that is going to be 50 squared, and from this you may get the f sub h equal to, take this one up, 5 over 10 and then 50 square. So it's going to be cut this one with 2. That is going to be half of 2,500. So f sub h is going to be 1,250 kilonewton. This is going to be the horizontal force, which is going to be equal. This horizontal force is going to be equal at any point of the cable. So now our equation will be y equal to 5 over 1,250 x squared. And you may write again y equal to, this divide this is going to be x squared divided by 250. So you get the cable equation that's going to explain you the shape of the cable along the bridge. And you also can use this equation to determine the length of the cable by integration this along the length, okay? And also by doing this, you may find the slope of the cable. Okay, the slope of cable is a form of what? dy by dx. And then you get what? You diff this equation by dx, diff x squared over 250. And then you will get this for x over 125. So that is going to be the slope of the cable. Okay, now we come to find what they ask us to do. The first one, they ask us to determine one point A. They ask us to find T at x equal to plus 30 meter. Okay, and by the f sub h is equal to all the length of the cable. And if the cable is here, and then you have this as the tension, and you know the angle over here is theta, you may have the T cos theta is going to be the force in the horizontal direction, and this is going to be f sub h. So by this equation, we have T equal to f sub h, T cosine theta equal to f sub h. And then you may have T equal to what? Equal to f sub h divided by cosine theta. And now, from the previous calculation, we get this already for 1250 kilonewton. So you can determine T any x when you find the theta. Okay, so the T at x equal to 30 is going to be 1250 kilonewton divided by the cosine of theta at x equal to 30 meter. Okay, so we got to determine the cosine as the theta when x equal to 30 meter. Okay, by using this slope equation, we may say that the tan theta is equal to x divided by 125. If you are looking for the theta at x equal to 30, so this equation gonna be tan theta at x equal to 30 is the 30 divided by 125. Okay, and if you do the calculation, you may get the theta at x 30 equal to. Okay, just stop the clip and put things into your calculator. Check what do you get from the theta here. We will get it for 13.495 degree. Okay, now you can find the T. Okay, the required the T at x equal to plus 30 meter is going to equal to 1250 kilonewton divided by cosine of 13.495 degree. And if you put it into your calculator, what do you get? It's going to get larger than 1250. It's going to be 1285.5 kilonewton. So that is the first one we have. You may put this answer into that. Next, 1.b. 1.b you require to find the minimum. Okay, you find the T min. Okay, and you also T min occur. T min is occurred at theta min. Okay, and from the equation you may see theta min, okay, will occur when the x, okay, when the x equal to 0. So that means if you prove this, you may see this is going to be tan theta at x equal to 0. That's gonna equal to 0 divided by 125. So the theta is going to be 0 degree, and this is gonna occur at point O, origin, because x equal to 0. So by doing this, you will get the T min equal to f sub h, and it's going to equal to 1250 kilonewton. And if you like to expand this, you may cut this and draw the free body diagram of this part. Okay, and you may see under this external force of 10 kilonewton per meter, and you also have this force of S sub h, this is B sub x, and this is going to be B sub y, and you may have this one at point O of what? Of F sub h. See, summation of x sub x equal to 0. You get the force at this point equal to F sub h or B sub x. So the minimum is going to be here. So next we are going to find the diameter. Okay, 1.3. Okay, we find the D, diameter of the cable. The diameter of the cable will determine based on T max. Okay, because T max going to produce sigma max, and by sigma max we will determine the required area. So we still don't know what the T max will occur, but for sure, as I mentioned before, the T max will be these 2 points, okay, with the theta max. So the T max will occur at x equal to 50 meter. When that occur at 50 meter, we can determine the theta. Okay, so the theta at x equal to 50 meter from this equation is going to be arc tan, inverse of tan of what? This one, x is 50, and then it's going to be divided by 125. By doing this, you will get the theta on this point, the theta on this point to be 21.8 degree. So this is going to be 21.8 degree, the theta, this T max going to occur. Okay, so the T max you may put into this equation. The T max is going to be what? It's going to be F sub h. It's going to be 1250, and then divided by cosine of 21.8 degree, and you will get T max equal to 1346.3 kilonewton. That is going to be the maximum, right? Because the minimum is 1250, and at 30 is in between, is 1285.5. So next we are going to find the diameter. So from the mechanics of material, we have what? We have sigma max. Sigma max gonna be T max, okay, divided by the A required. And then you may say A required is going to be taken up is going to equal to T max divided by sigma max. And sigma max can be as high as what? Can be as high as only sigma allowable. So this one gonna change to T max divided by sigma allowable. And we also have sigma allowable, right? Yes, it is 100 megapascal. So this one gonna be what? 1346. Okay. And you may put it like Newton. And then you may divide this by the 110 power 6 Newton per square meter. So you required area can be 1, 2, 3, 4, 5, 6, 1.346 and then divided by 100, right? 100. This 1, 2, 3, 4, 5, 6. Okay, so this one gonna be 0.01346 meter square. And if you like to put it in millimeter, if you like to put it in millimeter, you may put this one as 1, 3, 4, 6 Newton divided by 100 Newton per millimeter square. So you're going to get this one for cut. 460, right? 460 is going to be 13,463 millimeter square. And you may have this one for pi d square over 4. Okay. And by doing this, you may get what diameter. Okay, you may put it into diameter and you will get the diameter of what? You may pause the quiz, pause the clips and do your calculator and you do calculation. You got this for 131 millimeter. Okay, you put this one diameter into 131. Also, the force as the x is going to be 1,285.5 and the minimum 1,250. Okay, the last one, they asked us to determine the vertical component of the reaction at support A. So what is the force here? Okay, and the force here due to the symmetry is also equal to the force here. That is due to the symmetry. So for one point D, we put this one in the 1 point D. 1 point D. Okay, we find the A sub y. Since the cable is symmetry, okay, about O, we may have that A sub y equal to B sub y. Okay, A sub y equal to B sub y. And what we have is by summation of the force in the y direction. Okay. Consider the free body diagram of the cable, we have summation of f sub y equal to 0. And then what we have is the a sub y plus b sub y. That is going to be equal to the total applied forces. That is going to be equal to 10 kilonewton per meter times 100 meter. So this cut. Since they are equal, so 2a sub y is going to equal to 1000 kilonewton. And finally, we get a sub y of 500 kilonewton. That is going to be the result of a sub y here. So by doing this, because this one for 100 kilonewton, and we have this one for 500 kilonewton, and this one also 500 kilonewton. And since the b sub x is equal to x sub h and is going to be 1250 kilonewton, you may prove that the T max here is going to be equal to the square root of what? Of 1250 square plus x square. If you put into the calculator, okay, you may obtain the same T max as we have it before here. Okay, that's we used to design the cable, and the diameter of the cable that we have is pretty big. Okay, if you can see this is 13.1 centimeter, so it's going to be about this size. Okay, about this size. Okay, that is the end of this clip. That's we study how to analyze the suspension bridge by using the concept of cable analysis. This cable is subjected to the uniformly distributed load. Okay, and you also have a chance to consider this model compared to the real structure, the George Washington Bridge in the US. Okay, this is the end of this demonstration of this example.